Hey everybody, it's Ripley back again. What we're going to be talking about today is integration by parts. Now, integration by parts is actually a fascinating technique of integration, and it's really your first technique beyond integration by substitution. And the reason that we have integration by parts is so that we can solve integrals like the integral of the natural log of x dx, or the integral of the inverse tan of x dx. Because if you think about it, remember, just go through your list. First thing, have you memorized the antiderivative of natural log of x? No. Do you see a u substitution? No. Is there any algebra that can be done? No. So what I need is a different technique. Now, integration by parts is so elegant, and it's such a tricky little technique. But it's also tricky to use. So I refer to integration by parts as the nuclear option. You do not want to use it if you don't have to, but sometimes you absolutely have to. So let me explain what it is. What it really is it's the product rule for integrals. So if you think about the derivative, this is going to get a little confusing here for a sec, so just bear with me. If I take the derivative of a product u times v, hopefully everybody sees that this is u, let's go dv over dx times, actually I'm going to use a simpler notation, which you guys might gripe a little bit about, but don't worry about it. Do you agree that this is u times dv plus v times du, right? So if I mess around with this algebraically, I can write this as u dv is equal to the derivative of uv. Again, this is just the product rule for derivatives plus v dot du. Now, if I take the integral of everything, I can do whatever I want to an equation as long as I do it to both sides. Hopefully you see that I easily get to the integral of u dv is equal to, well, the antiderivative of the derivative of the thing is just the thing. So I end up with uv, wait a second, what did I do here? This should have been minus. Don't listen to me, I'm a fool. This should have been minus, sorry about that. So minus the integral of v du. You can see where that's a minus, right? I just sent this term across to the other side. Sorry about that. All right, so what this says is, if I can identify a u and a dv that are being multiplied by each other, and don't freak out yet, I'm going to show you some stuff as I work through this lesson, then I can rewrite the entire thing as uv minus the integral of v du. Now you may say, Ripley, what are we doing and why are we doing this? Remember, every technique of integration is to take an unsolvable integral and turn it into something that we know how to solve. So, for example, let's look, I'm going to change color of pen so we can play with the natural log of x. Let's start with that. So I take the natural log of x dx. All right, and I want you to understand fully that integration by parts does not supersede any other technique. You have to figure out when to use them, where, and why. So look close. Do you agree that what I have is I have the natural log of x and I have a dx. So I have a product of two things, even though this dx is largely symbolic, right? It's the width of the subinterval. It's the thickness of the rectangle. But I can say, okay, I'm going to let u equal the natural log of x, and I'm going to let dv equal dx. Now, the reason I do that is if you look at this formula, I identify a u and I identify a dv. Now you may say, wait a second, is dv going to always be dx? Not necessarily, and I'll work through a problem with you here in just a sec. So look close. I've got a u and I've got a dv, just like the formula told me to find. Now, to make the formula hum, I have to have a v. So how do I get to the v? Well, how do I get from a dv to a v? I take the antiderivative. Not only that, but I need a du. How do I get from a u to a du? I take the derivative. So du is equal to 1 over x dx, and v is equal to x, right? The antiderivative of 1 dx. Remember that dx is still the thickness of a subinterval, which I need because I'm going from dv to v, which requires me to take an antiderivative. Excuse me. Ooh, that was glorious. All right, now let's get into green mode. Avocado green, ugliest thing ever. Now I'm just going to follow the end of my nose, uv, v du, right? Integral of it. So I go uv, which is x, ln of x, minus v du, which is the integral of x times 1 over x dx. Well, it should be relatively obvious that this becomes x ln of x minus the integral of 1 dx, which is simply x ln x minus x plus c. Yay, that deserves a smiley face because it's so beautiful. All right. Now, where else might I use this? Well, let me show you. Let's do the integral of x e to the x. A simple one. Innocuous enough looking, right? There's a problem though. I can't do a quick and easy use substitution. I haven't memorized it, and there's no algebra to be done. But my spidey sense tingles because this is a product, which kind of tells me, hey, wait a sec, maybe this is an integration by parts setting. Think of it as an integration by parts setting. Now, what am I going to let be u, and what am I going to let be dv? Remember again, the formula tells me identify a u and a dv that are being multiplied together. Well, I am simple country folk, and I'm always trying to head in the direction of a simpler integrand. So if I, in my head, because I've been taking derivatives and integrals for a while, if I let u equal x, I know that du is going to be 1 dx, which, hey, du is going to turn into dx, which is, at least it's simpler. I may be wrong. It certainly wouldn't be the first time that I was. Excuse me. But what it does is I want this second integral. I'm going from u dv to the integral of v du. I want the second integral to be easier. I want it to be simpler. I often refer to this in class as funneling of an integral from a difficult integral into an easier integral that we've memorized. Okay? So if u is x, then dv has no choice but to account for the rest of the integral. So it has to be e to the x dx. Hey, that's kind of cool. Let's see what happens. So to get from dv to v, I take an antiderivative. To get from u to du, I took a derivative. I'm not going to say integration by parts isn't confusing. It is. So don't forget to take deep breaths and remember where you're headed. Remember what you're doing. Let the notation tell you what to do. To get from dv to v, antiderivative. So I get an e to the x. So this integral becomes uv, which is x, e to the x, not the integral of uv, just uv. See, easy to make mistakes. Even I make them. Minus the integral of e to the x dx, right? V du. And look at how much easier it is. It's x, e to the x, minus e to the x plus c. I could also write this as e to the x times x minus 1 plus c if I wanted to. Isn't that glorious and gorgeous? Not only is it glorious, it's gorgeous. It's gorgeous and glorious. Fantastic. Now, if I have a student in here and he's looking at me like I'm crazy. If I wanted to prove that this was truly the antiderivative of this, what could I do? Take a derivative. No, I'm not going to take a derivative because I'm not going to insult your intelligence. But it's relatively easy to see that if I took the derivative of this, I would get this integrand back again. Now, I did promise I'm going to do two more things. Let's take the integral of the inverse tan of x. And this should be relatively easily generalizable, if that's a word, to the other inverse functions. Notice what we're doing. We're filling in antiderivatives that we don't know. I mean, we know all our a to the x's and our e to the x's, but we don't have natural logs and we don't have inverse trigs. So we're doing that right now. Again, I'm going to let u and dv be two things. Why? Because that's how the formula works. Pick a u and a dv. Well, what should I let my u be? Well, should I let my dv be inverse tan? Well, if I let my dv be inverse tan, remember to get from dv to v, I got to take an antiderivative. Wait a sec. I'm taking the antiderivative of something that I didn't know how to take the antiderivative of in the first place. So the answer to that is wrong. So I'm going to let u equal inverse tan of x, and I'm going to let dv be 1 dx. Take the derivative, 1 over 1 plus x squared. Take the antiderivative, x. Stick this sucker in here. I end up with x inverse tan of x minus the integral of x over 1 plus x squared dx. Now, this gets really important, and I'll explain in just a second. I'm going to explain right now, there will be problems where you have to use integration by parts multiple times. I am going to break one of the bedrock laws of mathematics that says if you're going to let u equal something, those two things better be equal. Okay? But with integration by parts, because if you keep introducing new notation, it gets really confusing. So if you have to do integration by parts multiple times, then I'm going to let you use u and dv over, you can repeat u and dv, even though they're not going to equal the same things. Now, that said, this is not an integration by parts setting. This is a u substitution, right? If I let u, I can't use u because I already used u. So what I'm going to do is I'm going to use a. I'm going to do an a substitution. I'm going to let a equal 1 plus x squared. dA is going to be 2x dx. I don't need a 2x dx, so I'm going to do dA halves is equal to x dx. Now, why did I have to introduce a new variable? Well, because my technique was different. I'm using a different technique of integration than integration by parts. Had I had to use integration by parts again, I would have let you use u and dv again, but I'm not, so you can't. I know it seems like I'm picking nits with that, but I'm allowing you to do certain things to make your life easier, but I'm not going to let you abuse the language of mathematics too horribly. All right, so let's get through this. This is still x inverse tan of x. Isn't that cool how that uv requires no integration to produce at all? It's just a residual from the product rule, which is delightful. All right, minus, now this 1/2 sits out here, and I end up with dA over a, right? So this turns into x inverse tan of x minus, now this is going to be 1/2. I know that this is the natural log of the absolute value of a, but I'm not going to bore you, so I'm going to call this the natural log of the absolute value of 1 plus x squared plus c. I'm done. This is probably not your first guess for what the antiderivative of inverse tan of x is. If I asked you, what's the inverse tan of x? I doubt that you'd be like, oh, that's easy. It's x inverse tan of x minus 1/2 the natural log of the absolute value of 1 plus x squared plus c, Ripley. Yeah. No, you probably wouldn't have. Okay. Now, there's something called tabular integration. Let's talk about this, and then I'll be done. And tabular integration is your best friend. Okay? Tabular integration is just an easy cheater way, of using integration by parts. Now, this is the rule. The rule is, if you're going to use tabular integration, remember, this is still integration by parts. All right? No doubt about it. IBP, you know. If you're going to use tabular integration, what you want is you want a polynomial term, a poly term, and then times what I refer to as a cyclical term. And then, of course, we're going to have our little dx here. Now, what do I mean by cyclical term? What I mean by that is, excuse me, I want an a to the x, I want a sine of x, or I want a cosine of x. And the reason I want that is because if I take enough antiderivatives of these things, then I can always cycle back to where I started. In fact, with a to the x, if I take enough antiderivatives, or just one antiderivative, I get the a to the x back. Now you may say, but Ripley, there's a natural log of a along for the right. Well, who cares? It's a constant, right? If I take enough antiderivatives of sine, what do I end up with? Negative cos, negative sine, positive cos. Whoops, that's not right. Negative cos, negative sine. Where am I? Antiderivative, cosine. There we go. Cosine of x and then positive sine of x. See, it's cyclical. But really, truthfully, we don't necessarily need it to be cyclical, but it really makes our lives easier. Now, watch. Here's what happens. All right? Here's where you're going to see this. Say, for example, that I want to take the integral of 3x squared plus x, and then let's go 2 to the x dx. All right? Now, notice that what we have is we have a polynomial term, and then we have the cyclical term. Now, it is important. It's very useful, but the most important part is this polynomial term. Here's why. Watch how tabular works. I pick a u, and I pick a dv. Now, I'm always going to pick the polynomial term to be my u. All right, so this is going to be 3x squared plus x. I'll explain why in just a minute. The dv is going to be whatever's left over, so this is going to be 2 to the x dx. Now, what I do is I'm going to abandon the notation of integration by parts. What I'm simply going to do is I'm going to take derivatives until this term turns into a 0. So the derivative of 3x squared plus x is 6x plus 1. The derivative of 6x plus 1 is 6, and the derivative of 6 is 0. For every derivative I took, I'm going to take an antiderivative. So this becomes 2 to the x over the natural log of 2. This guy becomes 2 to the x over the natural log of 2 squared, right? Now, I got to take, because I took 1, 2, 3 derivatives, I have to take 1, 2, and a third antiderivative. I should put this in parentheses. This is the natural log of 2 cubed, all right? Now, the way tabular works is awesome. What I do is I'm going to move diagonally from the upper left to the bottom right, like this. Just draw little arrows. Apparently, I can't draw a straight arrow today because I'm catawampus on my thingy-dingy here, my tablet. All right, I'm going to put a positive here in parentheses. I'm going to put a negative here in parentheses, and I'm going to put a positive here in parentheses. And what that means is I'm not adding. I'm actually taking this term times a positive 1. On the next one, I go this term times a negative 1. This term times a positive 1. So watch how this just falls out. What it turns into is 3x squared plus x times 2 to the x over the natural log of 2. Now, times positive 1, but that's just ridiculous for me to have to write times positive 1, right? It's this term times positive 1. My next term is going to be minus by virtue of this negative 1 right here. This is going to be quantity 6x plus 1 times 2 to the x over the natural log of 2 squared. Now that's right here. Remember, this the rules of logarithms don't apply here. I can't drop this 2 in front because this whole natural log of 2 is being squared. Then my next term is plus 6 times 2 to the x over the natural log of 2 cubed. Now I'm out of terms because from this point hence every derivative that I take is going to be a 0, and then when I multiply I just get zeros. So this is where I get to stick in my plus. See, look what happened to my thingy-ding. Oh, now it's back. Glitchy, stupid thing. Okay, so bam, and I'm done. It's fabulous. It works amazingly. Now, let me tell you why we do tabular integration. If I wanted to, put this back to black. If I wanted to, I could actually do, I'm not going to do it because you guys would hate me, 2 to the x and dx. If I wanted to, I could do parts on this. I could just do regular old integration by parts. The problem is I would have to do it not once, not twice, but 3 times. I would have to go through this whole god-awful uv minus integral of v du. This stuff, I would have to go through it 3 times, which is a bummer. All right? Tabular integration works because this term, this polynomial term, if I take enough derivatives of it, it disappears and it stops having an effect. Now, why do we want a cyclical term? What we really want is we want something that's easy to take antiderivatives of. All right? Chances are, if this is a polynomial term or something silly, then I can just multiply the whole thing out, or I can use a different technique of integration, like integration by substitution. All right, but where we run into trouble is polynomial terms, time signs, coses, 2 to the x's, things like that. Now, tangents, it's not going to work. If I try to stick a tangent in here instead of a sine or a cos, the integral, the uv minus the integral of v du part of it, when I start taking these antiderivatives, all hell breaks loose. I end up with increasingly more complicated antiderivatives, which is exactly what I don't want. Remember, we are funneling our integral, going from more difficult to simpler. Okay? Now, I know this is kind of a quick little barnstorming exploration of integration by parts, but it's a good technique. It comes up a lot, especially with tabular integration. That's going to be your best friend. Okay? Thanks for listening. I appreciate it, and I will see you in class tomorrow. Have a good day.